Okay, so we're on the third study unit, and the topic is distributed software engineering. So we'll be covering the following learning outcomes: demonstrate an ability to identify, analyze, and evaluate various key issues that have to be considered when designing and implementing distributed software systems, have a thorough understanding of the client-side computing model and the layered architecture of client server systems, demonstrate an understanding of various commonly used patterns for distributed systems architectures, and have a thorough understanding of the types of system to which each architecture will be applied or applicable. Have a thorough understanding of the CLAWS software as a service and how it provides web-based access to remotely deployed application systems. Okay, so there are these main types of systems that exist. We have personal systems, and these are not distributed. These are standalone systems that you may use on your personal computer or on your workstation. Okay, they do not do any remote processing capabilities, so to say. Then we have embedded systems that control hardware, and these embedded systems run on a single processor or an integrated group of processors. Okay, so there's a lot of localized processing for embedded systems. Then we have distributed systems, where the system software runs on a loosely integrated group of cooperating processors linked by a network. And that's our topic for today. We're focusing on these distributed systems and how they are applicable in terms of enterprise environments. So then we say a distributed system is a collection of independent computers that appears to the user as a single coherent system. So the user, when the user is using it, they under the influence that this thing is one system, but in actual fact, the way it operates, it's a more in a distributed manner behind the scenes. Obviously, you cannot see this because you're sitting in front of the system and you're using it. However, it is more decentralized more than anything. So distributed systems are decentralized in the way they operate. Okay, and I'll explain that in the next slide. Information processing is distributed over several computers rather than confined to a single machine. Okay, so the processing of information happens at different sites, different locations. Distributed software engineering is therefore very important for enterprise computing systems. I just want to show you guys this picture in the next slide. Now, in terms of a distributed system, we would still have our servers present. Okay, we'll still have our servers, and our servers are there obviously to serve us with resources and to manage our resources, our data resources, our printers, our files, and so forth. Okay, so our servers do some sort of processing. However, through the use of a network, the workstations and the personal computers in a distributed system have the capacity to help, okay, to help the servers in terms of processing. Later on in the lesson, we're gonna talk about these legacy types of networks where the processing capacity was purely provided by what we call a mainframe or the server, okay? And the clients didn't do anything. So when you're looking at a distributed system, it's still more or less operating as a client-server architecture. However, it's client-server with added processing capacity because the workstations, the computers that are connecting to the server have the ability to process locally, have the ability to store files locally, and run their own operating systems as well, which sort of relieves some of the stress from the servers, okay? And These are some of the characteristics of a distributed system. There's resource sharing. So all the computers, remember when you're talking about a system, you're talking about an ecosystem of, it could be a grouping, rather in simple terms, a grouping of multiple applications. That's the system, okay? So the system is never a one thing, it's a grouping of multiple things. And so if you picture it that way, we have all of these applications, okay? All of these applications, all of these hardwares, multiple workstations, multiple personal computing devices, all of them contributing their resources, okay? And the whole point here is that we grow that data in a more efficient manner. And also openness, okay? So when it comes to distributed systems, it has to be open to equipment that comes from, whether be it software, hardware equipment, or software manufacturing vendors. It has to come from different sources. So the distributed system cannot discriminate. It has to accommodate for everyone. And we're going to talk about how that is done later on. And what I mean by that is, it doesn't matter if somebody wants to come with a personal computer that's running a different operating system. They still need to be able to participate in the distributed system. So typically a distributed system is never one framework. It's never .NET only or Linux only. It's usually a combination of many frameworks together. And also concurrency. When you talk about the concept of concurrency, the ability to execute multiple simultaneous transactions. And that is good when we have multiple sites of processing, okay? We can do concurrent transactions. If there's only one point of processing, then what normally happens is that we have collisions, because you find that machines tend to sort of clash in terms of the processing time, that they want to all make changes to the same pieces of data at the same time. So that's why we're experiencing all of these clashes. So with distributed systems, we have concurrency due to the localized processing capacity. And also the ability to scale. So when the company grows, we can add more clients, and that obviously converts to that converts to more processing power, because we're adding new resources to the distributed system. And it's also fault tolerance, okay? By that to mean, if one particular computer goes down, it does not affect the whole system, the other points of the system, okay? Although there are multiple points of failure, but it's very easy in a distributed system to isolate any problematic node, and the rest of the network is able to function. So what are some of the complex issues that were experienced by distributed systems? They are more complex than systems that run on a single processor. Complexity arises because different parts of the system are independently managed, as is the network. There is no single authority in charge of the system, so top-down control is impossible. And remember that in a typical client-server architecture, where the server is the only one that does the processing, the server's role is also to enforce security management. So here we have computers that we've given authority. In a distributed system, there is authority amongst the client computers for the mere fact that they do processing and they store data. It means you're giving them authority. And with that authority, you need to be able to handle it security wise. So since we described them as independent computers, they're independent, although to some extent they may be storing their data on a server, but they operate in an independent manner, and hence it's a big complex challenge to enforce security. And so the challenge or the issues are more based on how do we control this thing, because it's branched out into different sites. So some of the other issues that we may experience when it comes to these distributed systems is transparency. Okay, we have to not compromise the end user's experience. Okay, as much as this system is distributed, but to the end user, it must appear as if, and it must operate as if it is all coming from one particular processing system. Okay, and usually that's not the case. You're going to experience some sort of latencies and delays because maybe the data that you're trying to retrieve is residing on another computer. Okay, so there's always those delays, and you need to ensure transparency. And then openness already described, where adopting a standard protocol can be a challenge. Okay, can be a very big challenge. Scalability, how can the system be constructed so that it is scalable? In terms of security, how can usable security policies be defined and implemented? Also a big challenge that I mentioned earlier. Security is everything in a distributed system, and it's very challenging, just like how it is on a peer-to-peer network. And quality of service, how should the quality of service be specified? How can you ensure quality of service when there are multiple points of failure? Okay. And also failure management, how can failures be detected, contained, and repaired? Because there are multiple points of failure, it can be a big challenge for you to identify where the source of the problem is. Okay, so what they are saying here, these are some of the design issues that you're going to experience when you are implementing these distributed software systems. So what is the role then of the middleware? The components in the distributed system may be implemented in different programming languages and may execute on completely different types of processes. Middleware is software that can manage these diverse parts and ensure that they can communicate and exchange data. Okay, so you can see here in the diagram, we have computer 1, 2, 3, and 4. Let's assume that computer 2 and 3 are sharing or on the same operating system, or they're running Windows, but computer 1 and 4 is running Linux. So because they're communicating through the network and they're running their own types of localized operating systems, we need something there to convert, okay? Because at the end of the day, it's all about the data. So the role of the middleware is to take all of these different applications operating on different platforms and convert them into a language that the localized software or the localized operating system will be able to understand, and it makes it more easier for the operating system to be able to store the data. So we say client-server computing, so distributed systems are accessed over the internet, are normally organized in a as client-server systems. And the internet is an example. When you access any application through the web browser, is an example of a client-server interaction that you do. So the user interacts with the program running on their local computer, which is, we call it a web browser or a mobile application. This interacts with another program running on a remote computer or a web server, okay? The remote computer provides services such as access to web pages, which are available to external clients. And the two examples they use here, they say a web browser and a mobile application. And these two are critical examples of three-tier architecture, okay? Because as much as you are using the client software, you're still connecting to the web server, which hosts the scripts, okay, the application scripts. And then from the web server, the request gets sent to a different layer, which is the database layer. And when we're talking about client-server architecture, there's no way we can leave out this comparison of thin clients versus fat clients. So what are thin clients? These are very old school, as you can see in the picture here on the right-hand side. That's an example of a thin client. So in a thin client model, the presentation layer is implemented on the client, and all other layers, such as data management, application processing, and database, are implemented on the server. So this thin client doesn't do any, it's just a It's just a terminal that connects you to the server and allows you to access data, applications, and so forth. Okay, that's all it does. And another term for it, we call it a dumb terminal, for the mere fact that it does not store anything and it does not process anything. Okay, and then we have the fat clients, which is the ones you normally see in a distributed system. Guys, earlier that the one distinguishing factor between the typical client-server architecture and the one that you see in a distributed system is the fact that there's localized processing and there's localized operating systems and there's localized memory as well and storage of data. So with the fat client, where some or all of the application processing is carried out on the client, data management and database functions are implemented on the server. Okay, so you'd see this one on a distributed system as opposed to these thin clients. And when it comes to the different tiers, with 2-tier, the one that would use the thin clients, you can see the squares represent the server and the circles represent the client, and that's how the model will sort of be structured in terms of a diagram. And this is not efficient in terms, especially when you're talking about reuse, okay? Because you are bundling up the data layer and the business logic layer, and then it becomes a problem when you want to do software reuse. And that's why the 3-tier architecture was invented. Okay, so it was an improvement on 2-tier architecture where the client connects directly to the server and the application processing and the data management layer are bundled together. And so are the presentation layer. So it makes it difficult to separate one and reuse. But you can see that the problem is solved when it comes to 3-tier because when we remove this presentation layer and we just want to reuse this part here and we're going to implement a new presentation layer. So you can do that in this 3-tier architecture. So it motivates for reuse. And this is an example of 3-tier on a banking application, okay? Internet banking system. You're accessing your internet banking profile on the internet. You're on a web browser, and the web browser is it's a client software, and it's using the HTTPS protocol, and it's also your presentation layer where you see the application, okay? And then from there, your web browser is connecting to the web server, and it's getting all the scripts, okay? From here, all the scripts that execute your requests. And then the scripts have to call or make a call to the database server through obviously what we know as SQL queries, okay? So this is how a typical 3-tier architecture will operate in a internet banking system. Then we also have the what we call the N-tier, okay, which is more than 3 layers. So how do we move from, or what motivated the move from 3-tier to N-tier? Okay, so they would have wanted an additional layer for security purposes and for validation purposes. We know that typically we had presentation, we had application, and then we have databases in our 3-tier architecture. But with N-tier, they add this additional layer, data handling layer, okay, to ensure that we do not end up with dirty data. We need to validate at different levels. We will validate at the client side, which is not safe because usually when you're validating on the client side, you are using a programming language like JavaScript, which a person can, if they're smart enough, they can override it, okay, by switching off JavaScript on the web browser. So it's not a safe way. So you can't just only validate your data here. If somebody wants to hack you, then it's very easy for them to do so. So we add an additional layer to ensure that we check everything that was entered here, maybe an email address, and we really want to check at this layer that the person inserted an email address in that particular field, okay? So here also on the server side, the application processing layer, we're going to check again whether the email is valid. And then also on the database side, the field or the column at which we're storing this data in would also have to verify whether it's an email address. So this ensures that there's different levels of validation, and at the end we get high quality, clean data. And this is just also describing what I just said about the different layers of this N-tier architecture. So what are the different ways or the different methods for implementing a distributed system? Okay, so we have these particular options of implementing or architectural patterns for distributed systems. We have what we call the master-slave architecture, which is used in real-time systems in which guaranteed interaction response times are required. Look at the way a plane operates, okay? We have all of these sensors that are equipped onto the plane, and they report to the cockpit, okay? So in terms of master-slave architecture, aeroplanes would be a critical example, because remember it says which is used in real-time systems in which guaranteed interaction response times are required, okay? So critical real-time reports on incidents are required. Then we have our two-tier, which we just spoke about, simple client-server systems, and where the system is centralized for security reasons. There's no distribution here of resources. We say the central computer, the server is in charge of everything, all the resources and all the security policies. Then we have multi-tier client-server architecture, which is used when there's a high volume of transactions to be processed by the server. So the server here will be under pressure, high volume of transactions. And this is the one, the multi-tier architecture is the one that is adapted in the distribution system itself, okay? Hence, when we adopt it to the distribution system, we actually call it distributed component architecture, which is used when resources from different systems and databases need to be combined, or as an implementation model for multi-tier client-server systems, okay? And then we also have the peer-to-peer architecture, which is used when clients exchange locally stored information, and the role of the server is to introduce clients to each other. So with peer-to-peer, you can have no server at all, and that's a typical peer-to-peer. Each computer is its own server. So peer-to-peer is when a system is computationally intensive and it is possible to separate the processing required into a large number of independent computers. So when it comes to peer-to-peer, there is no server at all, okay? Each computer is in charge. It's similar to the distributed system, but it is more unsustainable. It's harder to manage, okay? And so there's a large number of independent computers. When a system primarily involves the exchange of information between individual computers on a network, and there is no need for this information to be centrally stored or managed, okay? There are obviously, just like that distributed system, there are security concerns when it comes to peer-to-peer systems. And the lack of centralized management means that malicious nodes can be set up to deliver spam and malware to other nodes on the network. You need to trust the other nodes that you're connecting to. You need to trust your peers. If, for example, your peer doesn't have a proper antivirus or an expired antivirus, then they're exposing you as well, okay? And they're exposing the rest of the data on the network. And you may end up losing maybe 50% of the data if half of the nodes end up going offline. As opposed to the distribution network, there is some sort of backup because there are still servers involved. It's just that the concept of distribution comes with the mere fact that the processing is done at different sites, that's all. Peer-to-peer communication require careful setup to protect local information. And if not done correctly, then this exposes other peers. Okay, so moving on to the next concept, which is software as a server. So if you don't want to go through all of this stress of setting up distributed systems, working with peer-to-peer networks, which are unsustainable for an enterprise. You can opt to go for software as a service. And you're going to use the cloud, and the cloud service provider will do all of this stuff for you, and you just pay a subscription fee. Okay, so software as a service involves hosting the software remotely and providing access to it over the internet. Software is deployed on a server and is accessed through a web browser. It is not deployed on a local PC. The software is owned and managed by a service provider or software provider rather than organizations using it. Users may pay for the software according to the amounts of use they make of it or through an annual or monthly subscription. So these are some of the benefits that you get, that you pay for what you use, okay? And when you experience a period where you're not under pressure, then you pay less, which is good for you, okay? So there is some sort of flexible subscription model. So key element of software as a service, and it's accessed through a web browser or sort of a localized machine. I think we already mentioned these key elements. Implementation factors for software as a service, okay? Configurability. How do we configure the software for the specific requirements of each organization? Remember that a software as a service is more of a generic solution. However, each organization will still have their own specific requirements as to how they want it implemented and the kind of changes that they may want to make. So one of the things you may want to do is obviously the customization. Create a profile for each organization. And also the aspect of multi-tenancy. How do you present each user of the system with the impression that they are working with their own copy of the system, while at the same time making efficient use of the system resources? I'll leave that one to the last slide. In terms of scalability, how do you design the system so that it can be scaled to accommodate an unpredictability large number of users? Fortunately for you, if you're subscribing to software as a service, this is not really your problem. Scalability is not your problem. You are paying someone to handle that risk for you, okay? So you sort of trust that they'll be able to scale you when you need those resources. So you can see that we have all of these different, we can call it them different organizations, and they're all accessing this software as a service online. So we have company profile 1, and company 1 has 2 users. Then we have company 2, which has user 3. Then we have profile for company 3. So each company must get their own profile. We see this, look at Office, the way Office 365 is set up, okay? Although there's different companies using it, but each company would have its own profile that speaks to the organization. So you need to ensure in terms of configuration, you need to ensure that the branding, okay, the branding speaks to the organization. The business rules are able to accommodate the company's workflow, database extensions, and then also access control for the different users in the organization. These are some of the key configurations you will have in mind when you're implementing a software as a service for a particular institution. Look at for example, something like a student portal, okay? If you have different brands, you can software as a service rent it from a different organization, but each organization would want to brand it to speak to its particular educational institution environment. We want to put our own logo. We want it to look like our colors and so forth. And business rules. We want it to speak to our business rules. This is the time students submit, the links should expire. All of those things should be able to be enforced through this platform. And database extensions, okay, being able to define or separate your databases to meet a specific group of users' needs, and separating your data into different tables, and also access control. We have people that are lecturers, we have people that are students. How do we ensure that they don't have the same level of permissions when they're logging into the system? So, and lastly, this is the aspect of multi-tenancy. Okay, and multi-tenancy is a situation in which different users access the same system and the system architecture is defined to allow the efficient sharing of system resources. Okay, so a tenant, someone who is renting something. And in terms of systems, we have a single tenant and we have a multi-tenant. If we're talking about a single tenant system, it means each brand will have its own application and its own database. Okay, own application, own database for storing data. But if you look at the multi-tenant system, we have the same application the users are gonna interact with. However, the data is then separated into different databases. Obviously, this one, the single tenant one, is the most efficient one and is the most reliable one, but also it's the most expensive one. Okay, and this one here is less reliable, but it's cheaper. Okay, so that's what we mean by multi-tenancy systems. So in conclusion, designers of a system must carefully choose the most suitable architectural pattern, and this should be done on the basis of considering performance, dependability, security, and manageability of a system. Distributed systems are also known as software as a service, and software as a service can be defined as a cloud computing service where several servers may gain access to the service provided in the cloud, obviously through the aspect of multi-tenancy or single tenancy access. Okay, so that is the third study unit, distributed software engineering. I see, Eugene, you have your hand raised. Yes, you may ask a question.